Hello there. In this video we're going to discuss a method that can be used to approximate the probabilities of random variables that are situated to distributions that are normal or can be approximated by normal distribution. So these methods will be used for both discrete random variables x that follow some symmetric shape or those type of distributions that follow a symmetric shape in the continuous case. So our goal is that these are normal or approximately normal. And if you want to figure out whether it's approximate normal or not, you have to go into some analysis. So we're going to assume that we have already came up with the conclusion that these distributions are approximately normal and that these approximations are good enough. Alright, to begin, what we're going to do is we're going to analyze the actual normal distribution and perform some integrals on that to see sort of where this empirical rule approximations are going to come from. So first off, recall that a distribution is said to be normal if it follows a distribution that is equal to 1 divided by the square root of 2 pi times e to the minus 1/2 x squared. Any horizontal shifts or scaling stretches of this function would be also considered a normal distribution as well. So let's use some software to approximate the areas under this curve. So for the distribution for normal, we're going to use Desmos to do all these approximations. So let's consider f of x is equal to our PMF, so 1 divided by the square root of 2 pi times e to the minus 1/2 x squared. So this is our normal distribution. So let's find the integral from minus 1 to 1 of f of x dx. So remember, for the standard normal distribution, the standard deviation of this curve is 1. So this integral represents the area under the curve from minus 1 to 1. And since the mean is 0, this is also equivalent to finding the area under the curve from one standard deviation from the mean. So the probability that you're within one standard deviation of the mean, if you're distributed normal, is approximately 68.27%. Similarly, we can go the integral from minus 2 to 2. So that's going to be 2 standard deviations from the mean for a normally distributed random variable. And we see that's equal to 0.9545 approximately. And similar from the integral from minus 3 to 3 of f of x dx, that's within 3 standard deviations. We have 0.9973. And we can continue this further. So say the integral from minus 4 to 4 of f of x. And that pretty much gives us 4 nines. So if we go slightly above 4, so let's go to say 4.1. So 4.1 standard deviations from the mean. This will round up to 1 if we consider 4 significant digits. So within about 4.1 standard deviations from the mean, you pretty much have 100% of the data. And these three integrals, integral 1, integral 2, and integral 3, are pretty much where the empirical rule originates from. And these approximations can be generated from, say, Riemann sums, Gaussian quadrature, or whatever approximations for integrals that you may know. So now let's look at it from a non-calculus perspective. So what the empirical rule does is it takes those three integrals and combines them into one rule. So let's draw a normal distribution, and let's assume that this is the mean mu. And let's draw 2 points around it symmetric, and let's assume this is mu minus sigma and u plus sigma. So the empirical rule states that this area, shaded in blue, is going to be approximately 0.68, or approximately 68%. And from the integral, we saw that that's 0.6827, so 68% is an easy area to know. Then let us go out to, say, mu minus 2 sigma, and mu plus 2 sigma, so 2 standard deviations from the mean. So this area here in purple, the empirical rule says is approximately equal to 0.95. We saw that the integral was equal to 0.9545, so 95% is a good number to memorize or approximate that as. And if we go to mu minus 3 sigma and mu plus 3 sigma, so now we're pretty much on the tails. So if we consider this red region, which covers practically all of the distribution, so this area is approximately equal to 0.99. Some people add a 7 here for more accuracy. Because the integral from minus 3 to 3 of the standard normal came out to 0.9973. So the empirical rule says, sometimes known as the 68-95-99 rule, pretty much gives you an approximation for the area under a normal distribution between some standard deviations, or k standard deviations, where k is equal to 1, 2, or 3 standard deviations from the mean mu. So some basic probabilities associated to a symmetric or normal distribution is the following. So everyone should know this property. So if you're larger than the mean, then this area here is going to be 0.5, and this area to the left of mu is also going to be 0.5. 1 because it's symmetric, and 2 the area underneath the entire PDF must be equal to 1 for it to be a probability density function. So these two properties are obvious. Now let's start to mix the empirical rule approximations into this picture as well. So let's consider a normal distribution. So this is going to be mu. Now we're going to consider one standard deviation from the mean. So let's draw some lines here. It's not really symmetric. Let's scale that out just a bit more. This looks a little bit better. And my curve's not really symmetric either, is it? Yeah. I'm not a very great drawer, as most of you probably have already figured out. Alright, so what we want to do is figure out, okay, what is the area in each of these little regions? So the empirical already states that the area within one standard deviation from the mean is approximately equal to 0.68. So if this is the case, then the area within one of these little gray-yellow regions is going to be half of 0.68 since it's symmetric about the mean. So that means this area right here is going to be equal to 0.34, and this region right here is going to be equal to 0.34 as well. So with that being said, what about these little tails? So greater than one standard deviation from the mean and less than one standard deviation to the left of the mean. So if this area is approximately equal to 0.68, then the left, so what is 1 minus 0.68? This is going to be 0.32. So this is going to be half of 0.32, and this is going to be half of 0.32, since we're splitting the complement of 0.68 in halves, the left tail and the right tail. So that's going to be equal to 0.16 approximately. So that means this area right here is 0.16, and this region right here is 0.16. So we can find that 0.16 plus 0.34 is a half, and 0.34 plus 0.16 is a half, and a half plus a half is 1. Now we've partitioned our distribution into the left tail, right tail, and the one standard deviation segments of this distribution. And we can continue this for the two-dimensional case. So let's work out that. So let's make it a little bit bigger. So this is going to be mu. This is going to be mu plus sigma, mu minus sigma. Let's go mu plus 2 sigma, and mu minus 2 sigma. So let's consider the area within this region. So the empirical rule says that the area between two standard deviations from the mean of a normal distributed random variable is approximately equal to 0.95. So if that is the case, let us assume we split that area in half. So this region is going to be half of 0.95, and this is going to be half of 0.95 as well. So what is half of 0.95? So we can find that's approximately equal to 0.475, or 47.5% of the data there. 0.475. All right, so let's break this up into little pieces. So if that is the case, what would this region here be? All right, so previously from the empirical rule, we already know that the error within one standard deviation is 0.68. So remember that we found that this region here is 0.34, right? So that's 0.34 and this is 0.34. So if that is the case, well, we already know that this is 0.475 in this region here. So we can find the area of these individual pieces. So no, that's not 0.475. That's what we're going for. So what is the area in these little yellow regions? So that's a very basic equation. I'm going to call those areas x. So we know that x plus 0.34 must approximately be equal to 0.475. So these individual regions is going to be 0.475 minus 0.34. And that is going to be approximately equal to about 0.13, let's see, 0.135. All right, so each of these little pieces, this is 0.135 and this is 0.135. And then you can find, as an exercise, what these little pieces here say y is. Because we know y plus 0.15 times 2 plus 0.34 times 2 must be equal to 1. Or 0.34 plus 0.135 plus y must be equal to a half. So you can figure out what each of these individual tails would be equal to. So that's a useful decomposition. So if we look at the entire distribution and what we've done up to this stage, so if we're in 2 standard deviations from the mean, so here's our mean, here's 1 standard deviation, 2 standard deviation, 1 standard deviation, 2 standard deviation, so let's assume that's mu. Then this is going to be approximately equal to 0.34, 0.34, and this little segment is 0.135 and 0.135. And again, you can find out what that little area is if you want. And you can continue this for 3 standard deviations, so you can break up this region y into the 3 standard deviation region and this 3 standard deviation, because we know that this area is approximately equal to 0.997, and then you can use all the little tricks that we did before to figure out those things. So let's work out a couple examples where you may want to use the empirical distribution in the case that you don't have an integral calculator, or you don't want to approximate the integral, or you just want to have some rough estimates in case you're in the field and want to sort of get a guess of what's going on. So example 1. Let's suppose that the systolic blood pressure is normally distributed. Let us assume the mean is equal to 120 millimeters of mercury, and the standard deviation is equal to, let's assume, 3 millimeters of mercury. So let's find out what percentage of the population is going to be within 1, 2, and 3 standard deviations. So by the empirical rule, 68% of the population will be within 120 minus 3 standard deviations, or 120 minus 1 standard deviation, which is 3, and 120 plus 1 standard deviation, which is plus 3, which is the interval 117, 123 millimeters of mercury. So you have a 68% chance of randomly selecting a person and their blood pressure being between 117 and 123, approximately. This is not an exact thing because the empirical rule just gives us a rough approximation. If you want the exact value, you would have to do the actual integral up to, however many decimal places you want. So similarly, 95% of the population is going to be within the interval 120 minus 2 standard deviations and 120 plus 2 standard deviations, which is going to be equal to 120 minus 6, which is going to be 114, and 120 plus 6, which is 126 millimeters of mercury. So therefore, there's a 95% chance that you randomly select a person from the population and their blood pressure be between 114 and 126 millimeters of mercury. Similarly, 99% of the population is going to be within 120 minus, or 99.7%, depending on how accurate you want, minus 3 standard deviations, comma, 120 plus 3 standard deviations, which is going to be equal to 120 minus 9, which is 111, 120 plus 9, which is going to be 129 millimeters of mercury. Therefore, there's a 99.7% chance that a randomly selected person from the population will have a blood pressure between 111 and 129. Now, if you have problems, for example, like you're looking for 70% of the population, this can be used as a more rougher approximation for the interval. Remember, this is just approximation, so you can use this just to get an idea. If you're looking for, say, a 94% region, then this could be a good approximation. 98% would be between here. Now, if you're working with an interval that's sort of between 95 and 99, let's assume 97, you probably could choose this interval, or maybe even choose the average of these two boundary points as an approximation. Now, it's not going to be an exact region, and it's not going to be an exact probability, of course, but it's just there to sort of give you a rough idea of the percentage of the population that's between these two numbers. So let's do a second example. So let's suppose test scores are normally distributed what is the probability that a randomly selected score is within, or let's not do within, let's say more than 3 standard deviations higher than the mean. So pretty much what we're asking is, what is the probability that x is greater than or equal to mu plus 3 sigma? Now we're going to be looking for an approximation, so this actually should say what is the approximate probability. If we want the exact probability, we would have to use either an integral or, say, a normal distribution table to sort of give a rough approximation to that. So let's draw a little picture of what we're talking about here. So here's our test scores normally distributed. And we have our mean, which isn't stated, but that's not really important in this type of problem. So here's our mean, so half is to the left, half is to the right. Here's 1, 2, 3 standard deviations, 1, 2, 3 standard deviation. So we're interested in more than 3 standard deviations higher than the mean, not lower than the mean. So we're going to be focusing on this number. So our goal is to approximate this area here. All right, so let's draw a bar over here. So remember that the area between these 2 points, according to the empirical rule, is approximately 0.997. So if that is approximately 0.997, that means this region right here is half of that, which is about 0.4985. So remember, since half of the data is to the right of the mean, that means all of this over here is half of that. So the region here, which we're looking for, is going to be added to 4.985, and that's going to give us the value that we want. So that means the probability that x is greater than or equal to mu plus 3 sigma is going to be approximately equal to 0.5 minus 0.4985. So once we do that out, that's going to be equal to 0.0015, or a 0.15% chance of occurring. So that's just some basic approximations. If the distribution is approximately normal or exactly normal, and there's lots of tests to sort of see whether a population is normal or approximately normal or not, but that's not the video. So under these assumptions, the empirical rule can help you guess probabilities as long as you're a fixed number of standard deviations. If you want more exact things, either use a table or use integrals to find the exact value. Hope you enjoyed.